In this video, we intend to show how one can delineate a catchment, a basin area for a specific outlet point in QGIS. We start with a merged-dem file, which is a digital elevation model of the area, specifically of the island of Skiathos in Greece. Subsequently, we filled this DEM file, this merged-dem, with the Wang and Liu algorithm, which of course is to be found in the toolbox. We have the Wikimedia label layer with some info about the geography of the island, namely roads and main places, main villages of the island. The best way to do this is to start with a Staller order algorithm in the toolbox and demand the algorithm to determine the Staller order channels in the DEM, in the digital elevation model. And once this algorithm is executed, it shows the various channels of order 1, 2, 3, whichever order exists in the area. So, as we can see, the Staller order algorithm here shows us, first of all, we have to put it in the proper HEC-RAS system, which in our case is the Greek EPSG 2100, the Greek georeference system of 1987. We see 9 orders of existing in the island, from 1 to 9. But this is this of course contains very, very small channels, which are not very manageable, not very useful to what we want to do. Which means that now we have to explore from which order and on upwards the channels we should work with. So of course, perhaps everybody has noticed that Staller order 5 is already calculated here, but I will explore which order and upwards we have to keep the channels. So from raster, we must use a raster calculator, and to do this we use the algorithm Staller from the toolbox. We make sure that we save it to the proper folder, and then we have to tell the algorithm that the Staller order must be, we want it to be superior to 4 for the 4th order. So, of course, the chaotic dendritic situation that exists when we have from 1 to 9, we see that it is makes much more sense now when we have orders up to from 4 to 9, because we don't need the very, very small channels that exist. It's perhaps even better to check out the Staller order 5. Whether we have to choose Staller order 4 or 5, it's subjective. But me personally, I would prefer not to use the 4, but to go for the 5. So once we obtain this, we can forget the style order 4 layer, remove it, and keep the style order 5 layer, raster layer, and work with this. So the next step is to determine the upslope area for a specific point, which of course I will take a random point here, but it has to be, for a specific study, it has to be a specific point of interest, which we can choose from, what interests us. Like if there is a region where we want to know the flow rate and whether this flow rate is discharged easily through the channel that exists in that region, of course we have to go to check the coordinates of the nearest point that exists within the streams that have been formed with the way that I've just explained. For example, if we can see the geographical map of a region and we see that this is a stream, we have an area here is supposed to be the point that interests us. We have to take the nearest point of the raster file of the Strahler order that we have formed, because otherwise the algorithm will have difficulties to determine the upslope area, the basin area that interests us. So in this way I have chosen a point in the west side, midwest side of the island. So once we have decided the point of interest and we have made a point file, shape file with this point, which is not necessary, all we have to do is to call the algorithm upslope from the toolbox, upslope area, the coordinates x and y of the point, fill them as the elevation file, deterministic 8 as the method, and we run the algorithm. Might take some time. So this is the upslope area, the basin. The problem is after putting it in the proper HEC-RAS, we see that everything is dark outside. All points outside the upslope area are black and inside are white. So we have to do properties. We have to change the render type to paletted unique values, and we have to go to transparency, and it's very important to do additional no data value 0, which means that all the values, all points with value 0 will be eliminated, will not be seen, and we can also put some transparency to the points with value 100 to demand the channels, the channel network in vector form. Elevation, of course, it's filled in always. Threshold we leave to 5 because it's we decided that streams with Strahler order higher than 5 interest us. We don't need flow direction, flow connectivity, Strahler order, drainage basins. We need channels, and the junctions might also be of use. We can leave them on a non-permanent file layer. On the contrary, the channels, we need them on a permanent file. So this execution of this algorithm might take some and it is done almost. So channels and junctions. Proper HEC-RAS for both layers. Smaller junction symbols. Blue color for channels. And we can now vectorize the upslope area, the basin, so we will have it in vector form. This is done with transformation of raster to vector. Upslope area, basin, so once the algorithm is executed, it gives us the basin, layer, a vector one, with the delineation of the basin in vector form. But in order to see it properly, we have to work a little bit on the properties of this layer. We have to change the topology of the vector layer. Properties of this layer. With 100, it's the basin area itself, and with 0 value is the whole area outside the basin area, which means that we have to eliminate from the file the points with value 0, delete it from the file, save the new file, and of course at this point we can determine directly the area of the basin by adding a field area, decimal number, geometry, dollar area, and we can see that the area is, for example, 4,004,561 square meters, which means 4 square kilometers roughly. So now we have the basin area and the channels, but we still don't have the channels of the basin in a separate file. For this, as we said before, we have to do vectors, geoprocessing tools, section, and we have to cut the channels layer with the basin vector layer and save it in another vector file, vector layer, with the name of basin channels. So in order for us to distinguish the channels of the basin from the rest of it, we can choose a higher width for the lines. And now we have everything we needed about channels and the basin area of the basin. So when we arrive at this point, we have quite a lot of information to conduct a hydrologic study to estimate the discharge as a function, for example, of the return period of a rainfall by taking into account the elevation distribution, the land cover of the area, the slope along the main channel, and of course rainfall data. Hopefully we can have for the area, about the area, the intensity, duration, return period equation. And once this hydrologic study, which is not part of this video, we obtain from this the discharge, and we can conduct a hydraulic study of the downstream part of the main channel to determine the water profile, the velocity distribution, the flood number as a function of the return period. And once we have the discharge, we can conduct the hydraulic study, but we need for this the cross sections of the downstream part of the main channel. This we can also do with the QGIS. So how is it done with QGIS? That is a very simple technique. If we have from the add-ins the terrain profile tool, we click on the terrain profile tool, we select the FieldM layer as our layer that informs about elevations, and we draw cross sections of on the main channel. Simply by clicking like this, we see the profile. We can see whether this the specific cross-section suits us, and then we can do table. We can obtain the data in the table. We can also do copy to clipboard with coordinates, and then in an Excel file we can paste the data. We will see just in a minute what these 6 columns correspond to. The first column must contain the name of the river, the second the name of the ridge, the third the name of the cross-section, and then X, Y, Z, which is already given by QGIS from the DEM. So all we have to do afterwards is to change this XS with the name of the cross-section. But we can take some more cross-sections. It would be also always nice to check whether there will be sufficient elevation, sufficient area of the cross-section, but this is indicative what we're doing here, so I will do a second cross-section here. And then another 2 or 3 cross-sections. Table, copy, clipboard with coordinates. Third cross-section. The fourth cross-section. And the fifth cross-section. So now the Excel file, we have to fill the name of the cross-section. So from the previous seen Excel file, so from this Excel file, we replace, we put the river station at column XS instead of the name of the cross-section. In column C, we put the river station, that is the distance from the last downstream cross-section to the current cross-section. For every point of the respective cross-section, the same, and save the Excel file in .csv form. That's why we see here that we have for the first downstream, for the last downstream, the distance 0, and in column C, the second 22.50, which are the distance between the two. For the third is 43.82, 67.12 for the fourth, and 97.58 for the last fifth cross-section. We have here to make a remark that needs to be, we need to pay attention whether saving from Excel to CSV file, sometimes it has semicolons instead of comma. So we have to be sure that there is a comma by opening, for example, the Excel file with Notepad or other software. And we are ready, the file is ready then to be entered into HEC-RAS with a complete geometry. Once the data, and we save the file. And we can now open the geometry. We have prepared the project. Skiathos, the island. Kathavothros is the name of the place. Geometry. import geometry data, comma separated value format, geometry CSV file, and SI metric units, finished import data, and we have our cross sections here. We see that by the coordinates it has prepared the whole geometry. We can see the cross sections here. Of course, there are data that we have to add, like the downstream ridge lengths, the Manning's N values, and the left and right station for overbank for the main channel. This is relatively easy, of course. With the tables, we can fill the Manning values. Let's put a unique 0.035 value in every cross section for the Manning coefficient. Ridge lengths separately for left overbank, main channel, and right overbank. Of course, there's a difference between the stations of the two cross sections. So here we have to put 97.58 minus 67.12, which makes 30.46. And then for the next cross section, we have to put 23.30. Completed the downstream ridge lengths for its cross section. We can proceed to run a flow. In this very brief example, we'll show a steady flow case. We can give up to 32,000 different discharges, flow rates. I will choose only one, we will show only one. So suppose that the hydrological study has resulted in a discharge flow rate of 32.5 cubic meters per second. We have to provide ridge boundary conditions. For simplicity here, we will suppose critical depth in the last downstream section, as well as in the first upstream section, and let HEC-RAS calculate the flow. We have to choose mixed profile flow regime because we are not sure whether flow regime is supercritical or subcritical with this flow rate. And we can check the results either in the cross sections or the profile of the water surface. We see, for example, that the flow is supercritical, and it becomes subcritical after the second, between the second and the third cross-section. There is a small hydraulic jump, and we can have all sorts of graphs, for example, of the velocity profile, which varies from 1.45 to 3.3 meters per second, and of course Froude number respectively from 0.7 to 2.2, the top width of the flow, etc. We can have the kind of 3D representation of the channel with the cross sections that we have provided. And of course, what we need mostly is the values of the flow parameters from water surface elevation, critical water surface height, the slope of the energy grid line, Froude number, velocity, etc.